Welcome to today's paper reading. Today's paper is titled, Rasterized Edge Gradients, Handling Discontinuities Differentiably. This paper was published on AR14 by Stanislav Pidhorskyi and colleagues from Reality Labs, Meta. The abstract highlights the challenges in computing gradients for rendering processes, particularly due to discontinuities and rendering approximations. A novel method is introduced, which uses the concept of microedges to simplify gradient computation. This method allows for a continuous, differentiable process without modifying the forward pass, making it applicable to various types of rasterized images. The method is demonstrated to be effective in dynamic human head scene reconstruction, handling camera images and segmentation masks efficiently. The main contribution of this paper is the development of a theoretical framework for approximating gradients in the rasterization process. This framework aims to improve the accuracy of gradient approximation over state-of-the-art methods. The challenges addressed include the discrete nature of rasterization operations, particularly at triangle boundaries, which complicates gradient computation. To tackle these issues, the authors introduce a microedge formulation that interprets the rasterized image as a continuous process, thereby simplifying gradient computation and effectively handling geometric discontinuities. Differentiable rendering is crucial for various computer vision tasks, including 3D object reconstruction, prediction, and pose estimation. It utilizes diverse 3D representations such as mesh-based, implicit surfaces, and point clouds. However, mesh optimization presents significant challenges, and rasterization-based methods face issues with non-differentiable visibility at boundaries. The computational expense of ray tracing frameworks also limits their practicality in optimization-intensive tasks. The color of a pixel is calculated using the integral of the product of a 2D pixel filter K and radiants are over the domain D. For simplicity, the product K, X, Y, R, X, Y is denoted as F, X, Y. The focus is on the gradient of the loss function L with respect to scene parameters phi, which is computed using the chain rule. The incoming gradient from the loss function is typically computed by automatic differentiation. The goal is to determine how the pixel value changes with respect to the scene parameters. The differentiation of the integral of f, x, y is broken into two parts using the product rule, considering the partitioning of f into two continuous functions fa and fb. The EdgeGrad method is built on several core assumptions. First, the rasterized image is treated as the result of a continuous process that aligns with discrete pixel rasterization. This is achieved through the use of microedges, which are small edges positioned exactly between pixels. This approach allows for local gradient estimation, simplifying the computation. In edge detection, the method analyzes pairs of adjacent pixels using the Heaviside step function to account for discontinuities. It handles C1 discontinuities by averaging one-sided limits of derivatives. For gradient scattering, the method backpropagates gradients to fragments and classifies edges into types such as no edge, adjacent primitives, overhanging primitives, and intersecting primitives. This classification helps in accurately scattering gradients to the relevant fragments, including handling complex scenarios like geometry intersections. Figure 1 demonstrates the concept of microedges and their impact on pixel intensities. It shows how the construction of microedges affects the change in pixel intensities A and B as the edge position P moves. The figure highlights a C1 discontinuity at P equals 0, which is not present when considering the average intensity. This visualization is crucial for understanding the gradient computation process and rasterization, particularly how edges between pixels influence the overall image formation. Figure 2 illustrates the gradient computation flow, focusing on the backward propagation process. In this process, gradients originating from the loss function are traced back and distributed to the fragments. This approach ensures that the gradients are accurately propagated through the network, allowing for precise adjustments in the model parameters. The figure highlights the edge-centric nature of the gradient computation, where gradients are first computed with respect to the edge positions and then transformed into gradients with respect to the fragment positions. This method is crucial for maintaining the integrity of the gradient flow and ensuring that the model can learn effectively from the data. Figure 3 illustrates the edge classification process used in our method. The edges are categorized into 4 distinct types: no edge, adjacent primitives, overhanging primitives, and intersecting primitives. In the overhanging scenario, the foreground fragment directly controls the edge's movement, with a derivative of 1. For intersecting primitives, the relationship between fragment movement and edge displacement is more complex, involving both positive and negative derivatives. This categorization is crucial for accurately computing the gradients with respect to fragment positions, which are then backpropagated to vertex positions. Figure 4 illustrates the geometrical derivation for the partial derivative del p/del r, which is essential for converting edge-related gradients to fragment-related gradients in scenarios where edges are formed by geometry intersections. The figure focuses on the XZ plane, where the render camera views the scene along the z-axis, resulting in edges that are parallel to the y-axis and perpendicular to the drawing plane. The projections of both intersecting primitives are transformed into 2 lines, facilitating the analysis of how the edge would move in response to infinitesimal movements of each fragment. In the experimental analysis, the performance of the proposed approach was first evaluated through forward gradients. These were compared against finite differences, showing that the method matches finite differences even in cases of intersecting geometry. The backward gradients were then quantitatively analyzed, demonstrating improved accuracy especially for complex intersecting geometry. Lastly, the runtime performance was examined, revealing that the method significantly outperforms other approaches in terms of running time while maintaining comparable accuracy to Mitsuba, especially at larger image sizes. Figure 5 presents a comparison of forward gradients across several test scenes, using finite differences as a reference. The figure includes gradients computed with a. Finite differences, b. Mitsuba 3, c. Redner, d. Diffrast, and e. Our EdgeGrad approach. Notably, EdgeGrad maintains alignment with finite differences even in scenarios involving intersecting geometry, a challenge where other methods like Mitsuba and Redner fall short. Diffrast, while generally noisier, assumes triangles containing silhouette edges always overlap pixel centers, which often leads to omitted gradients. Figure 6 presents a comprehensive analysis of the runtime performance and gradient errors of our method, EdgeGrad, in comparison to Mitsuba 36 and Diffrast 20. The figure is divided into 4 sections: A. Runtime measured in milliseconds, ms, as a function of image size in pixels, px. B. Runtime in ms as a function of triangle count, c. Gradient error percentage as a function of image size in px without self-intersections, and d. Gradient error percentage as a function of image size in px with self-intersections. Our method significantly outperforms other approaches in terms of running time across various image sizes and triangle counts. Despite comparable accuracy to Mitsuba 36, at larger image sizes, our method shows slightly worse performance at smaller image sizes due to subpixel triangles. This figure highlights the efficiency and accuracy of our EdgeGrad method in handling complex rendering tasks. Figure 7 provides a detailed overview of the experimental setup used in dynamic head scene reconstruction. It begins with the ground truth camera image, A, which serves as the reference for the subsequent steps. The predicted segmentation mask for the mouth region, B, is generated using HRNet 47, highlighting the specific areas of interest. The initialization mesh from 3DMEM, C, represents the starting point for the avatar mesh optimization process. The optimized avatar mesh, D, showcases the refined geometry achieved through the optimization process. The rendered image of the optimized model, E, demonstrates the visual quality of the reconstructed avatar. The rendered segmentation estimation image, F, shows the predicted segmentation after optimization. The learned static segmentation texture, G, is crucial for maintaining consistency in the segmentation across different views. Finally, the initialization meshes and optimized meshes for the Blender dataset, H, illustrate the progression from initial rough meshes to the final detailed reconstructions. Figure 8 presents a comparison of inverse rendering reconstructions using our method, Diffrast, and a method without edge handling. While diffrast effectively matches object outlines, it exhibits issues with interpenetration, particularly noticeable in the leaves of ficus. Our method, however, excels in capturing finer details, as seen in the backrest of the chair and the ground of the Lego scene. In stark contrast, the method lacking edge handling fails to reconstruct these objects effectively, highlighting the critical role of edge handling in achieving accurate and detailed reconstructions. Figure 9 showcases example renderings of mesh-based avatars that have been trained using EdgeGrad. These avatars are capable of capturing complex inner mouth movements, including the dynamics of teeth and tongue. This level of detail is crucial for realistic facial performance capture, demonstrating the effectiveness of the EdgeGrad method in handling intricate geometries and non-Lambertian materials. Table 1 presents the accuracy of backward gradients, specifically the relative error percentages, for various methods applied to test scenes. The table highlights the performance of methods like Redner, Mitsuba 3, diffrast, and EdgeGrad, our method. Notably, the second and third scenes include geometry intersections, which accentuate the EdgeGrad method's capability to handle such complexities more effectively compared to other methods. This table is crucial for understanding the comparative efficiency and accuracy of gradient computations in complex scene scenarios. Table 2 presents the per-scene quantitative results from the realistic synthetic Blender dataset, which includes scenes with complex geometries and non-Lambertian materials rendered using Blender's Cycles Path Tracer. The table features metrics such as PSNR, SSIM, and PIPS, comparing our method, EdgeGrad, with diffrast and a variant without edge handling. Notably, the inclusion of intersection handling significantly enhances the PIPS score, indicating a reduction in topological artifacts that minimally affect PSNR and SSIM but significantly impact perceptual quality. In this section, the authors demonstrate the significance of accurate edge gradients in a head modeling application. They fit a personalized mesh-based avatar representation to facial performances captured in a multi-view light stage. The avatar creation method is modified from a previous study. The facial avatar representation employs an encoder-decoder architecture to generate mesh vertices and texture-mapped appearance features, which are shaded using a pixel-wise MLP to produce RGB appearance. The process begins with a coarse face tracking produced using traditional computer vision, which serves as initialization for inverse rendering. Notably, this coarse face template consists of a small number of vertices, 8K, and lacks geometry in the interior of the mouth. Figure 10 presents a qualitative evaluation and ablation study on dynamic head scenes. The figure compares three different renderings: A. Ground truth images, B. Images produced by diffrast 20, and C. An ablated version of our method that excludes the segmentation mask. The avatar model used in this comparison is derived from 29 and was trained using EdgeGrad and diffrast techniques. The figure highlights artifacts in the renderings with white arrows, emphasizing the differences and improvements in detail and accuracy across the methods. The method presented in this paper provides accurate gradients across various visibility discontinuities, such as triangle edges, occlusions, and geometry intersections. This leads to enhanced mesh reconstruction fidelity across diverse inverse rendering scenarios, which is comparable to implicit and volumetric methods. However, the method inherits the constraints of rasterization, including difficulties in managing transparency, achieving precise anti-aliasing without multisampling, and the absence of physically based rendering and global illumination. Additionally, it may inaccurately interpret adjacent primitives in finely tessellated meshes, leading to subpixel triangles. Thank you for watching.